Today we're covering conditional statements, which is found in section 5.4 of your geometry textbook. So we're going to learn what a conditional statement is and learn how to write one. And then we're also going to look at what biconditional statements are. And then we're going to learn how to define and use symbols for the inverse, converse, and contrapositive of a conditional statement. So a conditional statement is just a statement where you have a hypothesis and a conclusion. So usually we use the symbol P for your hypothesis and a Q for your conclusion. So we can say if P, then Q. And then the notation, so you don't even have to write any words, would be P and then an arrow Q. You can also say P implies Q. So another word for a conditional statement is an implication because P implies Q. So the P represents the if or the hypothesis and the Q represents the then called the conclusion. So if we have the statement, there are no clouds in the sky, so it is not raining, and we wanted to write it in if-then form, we would write, if there are no clouds in the sky, then it is not raining. If the statement is school will be canceled if a blizzard hits, and we write that as an if-then statement, we would write, if a blizzard hits, then school will be canceled. So we also have these things called truth tables, and the truth table is it's columns and rows. So your first column is your P, your second column is your Q. So if your the way that you want to do your truth column, your truth tables is for this first statement, you do all possibles. You can have a true and a true and a false and a true, and a false and a false. So those are all possible outcomes. Okay, and then you look at the conditional. P implies Q. Is it going to be a true statement or a false statement? Is if your true implies your true. Well, because you have a true statement implying a true statement, it's going to be your conditional will be true. If you have a true statement that implies a false statement, your conditional, your implication is going to be false. If you have a false statement implying a true statement, it's going to sound a little bit ridiculous because it's going to have if something, that's not true, then something that is true. That's actually going to be true because even though your hypothesis is false, as long as your conclusion is true, then you have a true implication. And then the last one, if you have a false implying a false, well, because they're both false, that means it's actually true. So you would have a true implication for that one. So this is an example on how to do a truth table. So let's try an example. If horses had wings, then horses could fly. And then the next one is if ocean water is grade milk, then ocean water is a nourishing beverage. And then the last one, if whales walk, then 4 + 1 is 5. So in the first implication, we have a false implying a false, which means that that's true. On the second one, we have a false implying a false, so that one's true. And in the third one, we have a false implying a true, so that one is also true. So they're all true. So because every hypothesis, since each hypothesis is false, however, the first and second one, you also had a false conclusion, and then on the third one, you had a true conclusion. So the symbol forms, the first one was false implies false, because this was false and this was false. The second one was, again, false implies false, and then the third one was false implies true. So our next type of statement that we're going to learn is biconditional. So a biconditional is where you can take your conditional and go both ways. So if P, then Q, and if Q, then P. So one way to write that is P implies Q and Q implies P. But another way to symbolize that is double arrows. So P, double arrow Q. And then in words, you would say this statement, if and only if this statement. So the conditional P implies Q is the same as the disjunction not P or Q. So that's something to remember. So if you have P implies Q, you also have not P or Q. So let's do a truth table. So again, on your truth table for P and Q, you're going to list all possible outcomes. So it's either true and true, true and false, false and true, and false and false. So then you're going to do P implies Q because that's the first part of what we're trying to prove. So we'll do that part. So P implies Q. If either P and Q are true, then you have true. You're not P. So if P was originally true, not P is false. And then if you have not P or Q, so if you have not P and not P is false, and you have Q and Q is true, so you have false or true, that's going to be true. And then if you have P implies Q, that was true. And then you have not P or Q is also true. So you have a true if and only if true, then that means your final answer is true for this row. On the second row, you have a true implies a false, that's false. And then your not P is going to be, since it was true, your not P is false. And then your not P or Q. So not P was false, and your Q was false. So you have a false or a false, which is going to be false. It's the only option. So over here, you have P implies Q, which we said was false. If and only if, not P or Q, which was also false. So false if and only if false, well, that's a true statement. Logically, that makes sense. So on our next one, false implies true. That's true when you have P implies Q. Our not P is the opposite of P, so that will be true. And then not P or Q. So our not P is true, and our Q is true. So if you have true or true, then our answer is true. And then for our last part here, our P implied Q was true. Our not P or Q is also true. So a true if and only if true is true. So then we have false implies false. So false implies false is going to be true. And then our not P is true. And then our not P or Q is going to be not P is true and our Q is false, which means the or is true. And then our last column here, our P implies Q, which was true, and then not P or Q is also true. So true if and only if true, well, that's a true statement. So because our last column all is true statements, we just proved that if you have P implies Q, then you also have not P or Q. So that's what we just proved. We just proved this statement here using a truth table. So let's change this conditional statement to a disjunction. So remember, the disjunction is not P or Q. So if a child disobeys, then he will be disciplined. So we need to know not P. So P is disobeys. So not P would be not disobeying. So a child obeys. That's the opposite of disobeying. Or, because now we're going to do or Q. So, or he will be disciplined. So that's what we have there. Our next definition is converse. A converse of a conditional statement is where you switch the hypotenuse and conclusion. So if you have P and Q, the converse is Q implies P. And then you have what's called the inverse. You get that by negating the hypotenuse and conclusion. So if you originally have P implies Q, the inverse will be not P implies not Q. Then you have the contrapositive. The contrapositive is by doing both the inverse and the converse. So you're going to switch the hypotenuse and conclusion, and you're also going to negate both of them. So let's do an example. If we write the converse, inverse, and contrapositive of this implication. If we have a blizzard, then school will be canceled. The converse is switching it. If school is canceled, then we had a blizzard. The inverse is negating. So if we do not have a blizzard, then school will not be canceled. And contrapositive is doing both. You switch and you negate. So if school is not canceled, then we did not have a blizzard. So the contrapositive rule is that a conditional statement is equivalent to its contrapositive. That means that it's the same thing. So P implies Q is the same thing as not Q implies not P. All right, that's all. Go ahead and try some problems on your own.